Hi class, we are now on chapter 10.7. We're going to look at the shapes of molecules. This is going to be a little bit long because I have a lot of examples because sometimes this is a little hard to understand. So VSEPR, valence shell electron pair repulsion theory. This describes the orientation of electron groups around the central atom. So they are not just randomly thrown together. They are arranged in a specific way. This is because electron groups are arranged as far apart as possible because it's like putting a magnet together on the same side. They will repel each other. And molecules want to stay as stable as possible. So they will stay as far apart as possible, but still within a range that the structure is still strong or stable. This states the specific shape of a molecule, and we're going to determine that by looking at the central atom. So Lewis theory, which is why we're learning about Lewis structure drawing, with the VSEPR, we can use these two things to determine the shape of molecules. So it's all, again, based on electron groups, and electron groups is just a general term for lone pairs, single bonds, and multiple bonds. These are all counted as one. So it doesn't matter if there's lone pairs, single bonds, triple bonds, it's still counted as one electron group, and I'll go over that. The repulsion between the negative charges determines the geometry. So this is in a shape to minimize the repulsion of the electrons. So let's look at the first one. The easiest one to look at is carbon dioxide. And if you see here, we have two, now we're going to look at the center atom. So the center atom is here. So we have two atoms attached to the center atom. Now, based on what we can see here, we have two double bonds, but it doesn't matter. We count this as one electron group and one electron group. So it has two electron groups, and they will situate themselves as far as possible because they have enough room and space to do that. So this is a linear geometry, and it is a 180-degree angle. Where am I getting this information from? Well, I'll show you in the next slide. So again, this is just, I expanded more information about it, about the two electron groups, and to remind, oh, that cut off there, what an electron group means. It cut off all of this. Sorry about that. I took this slide from another one of my slides in another class. Two bonding groups. So this is one bonding group, two bonding groups. We're not looking at these specifically as single, double, or triple bonds or even a lone pair. We're just counting them as bonding groups attached to the center atom. So this is a chart that is in your book, and this is how we determine the shape of molecules. So what we need to do is look at electron groups. So these are electron groups. These are bonding groups. This is what's bonded to the center atom. And these are lone pairs that would be on the center atom. And everything is based on the center atom. So in this case, when we look at carbon dioxide, we have two electron groups attached. We don't have three because we're not counting the center atom. We're counting the atoms attached to it. So we have two electron groups, and they're also bonded. There are no lone pairs on the center atom. So 2, 2, and 0. This tells me that the electron geometry is linear, and the angle is 180, and the molecular geometry is also linear. When you don't have lone pairs on a center atom, the molecular geometry and the electron geometry will equal each other. So they will be the same. So in there you have an example of exactly the one that we just showed. So now we can go on to another one that's a little bit more complicated. It's formaldehyde. I should take a step back and explain this. Electron geometry is based on electron groups, the electron groups that are attached, so it counts lone pairs. However, molecular geometry does not. It only counts what's actually attached and ignores the lone pair that exists. So when there is a lone pair on some of these, for instance, like here, the geometries will not match. But when there are no lone pair, then geometries will match. So let's go on. So we have formaldehyde here. We have a carbon, and we have three electron groups attached, and they're all bonded, no lone pairs. So based on that, if we go back, we see three electron groups, three bonded, no lone pairs. This is trigonoplanar at 120 degrees, and trigonoplanar again. And you can see it's kind of trying to do a 3D. It's very hard to do this online because if you were in person, you would be building these in lab. So you can see the 3D of how these are actually situated because none of them are flat. not the way that we see in a plane of paper. But this is trigonal planar. Trigonal planar. So, oh, I went too far. So that's where you see it like this. It's 120 degrees this means approximately, so it might be a little bit off, but they're all equivalent. Again, here is from another slide. I just attached these because they give other pictures compared to what was given in your book. So these give a little bit different where you see it. This is as a Lewis structure. This is an electron group geometry. And then here is it in with the, the stick and the balls with the color coordinated to what that atom is. Okay, so we have methane. And you can see methane is here. And it's got this shape of, let me jump to it. The repulsion of the 4 electron groups, so 1, 2, 3, 4, around the center atom, causes the tetrahedral shape. So tetra is 4, allows the maximum separation among the 4 groups. So you see here's the ball here, and you can see there's one up, one to back, one forward, and one back again. And when you do it like this, this may give a little bit more of an idea of how this looks. So we write it on paper, but it's actually got 90-degree angles, so it's not flat. And I tried to find something that gives a little bit more. The end of your book talks about wedges. If you plan to go on to organic chemistry, you will be an expert at drawing these like this. So let me explain what this means. These wedges that are dark mean that this H is coming directly out at you. This dash means that this is going directly in the back. So if you look at this carbon, these look the same. This is in the plane of the paper, or if you're looking at a laptop, it's in the plane of the screen. That means that these are flat. This is coming directly at your face. This is going directly behind it. So that's trying to give you an idea that this is not flat. All right, so we've covered some that don't have lone pairs, but now we need to discuss ones that have lone pairs. We're going to start with water. Water has 4 electron groups on it because it has lone pairs, and we count them when we're trying to classify this. So 1, 2, 3, 4. Now we separate this. It only has 2 bonding pairs, and it also has 2 lone pairs. But when we look at an electron group, we do not care what it is. We just count it as an attachment. So in this case, it's got 4 electron groups. I'm going to jump to a chart. I have a chart here. There we go. So we go down to 4 electron groups, but we have 2 bonding pairs. So let's go where the 4s are. And we have 2 lone pairs. The geometry will not match between the electron geometry and the molecular because the lone pair throws it off. But this is a tetrahedral for electron shape, counting all the electron groups. And it's molecular when it is counted for the molecular geometry. Why is that? Because it ignores the lone pair. So it pushes these down on here. So let me go back up to the water. And it is a bent structure. So we have a lone pair here and a lone pair here. But what it's really not showing you is that this lone pair, there's one here and there's one here. The molecular shape is the one that determines the shape of the molecule. So and it's kind of weird because the bent shape is because of the lone pair, but we don't show the lone pair when we're dealing with molecular geometry. And see, it says it even here that there's reasons why the lone pairs influence this. Lone pairs take more space than bonds, and so they repel more. So if you can try to think of like Mickey Mouse ears, there's a Mickey Mouse ear here with a lone pair and a Mickey Mouse pair here. They push these down because of the fact that they take up so much space with 2 lone pairs on it. That's where the bent shape comes from. I might have no, I don't. I thought I had a picture of it. So when we draw them, you draw it flat like this. It's really more accurate to draw them kind of a lone pair here and a lone pair here, but we don't. More like this is how it actually is shaped. And now here's the bent wedge dash. This is flat. This one's coming directly at your face. That one's going directly behind it. So it's kind of hard to imagine, but this is a bent shape for the. It's a tetrahedral for when you look at the electron group geometry, but it's bent shape for the molecular. And here's SO2. Now this one's a little different because it has a lone pair, but it only has 1 lone pair. And So we can also look this one up. So if we look this up, we got 2 bonds, we have 3 electron groups, we have 2 bonds, and 1 lone pair. So let's look that up. So we go where it's 3s. So do we have 3 bonding groups? No, we do not. We only have 2, and we have 1 lone pair. So the electron geometry is trigonoplanar, which is 120 degrees, which is different than the other bent, because this is also bent, but it's also a different, there's a difference in the degree of the shape. And this one is 120 degrees, which is similar to the trigonoplanar. See the group that's here? This one doesn't count that lone pair, but that lone pair is so big that it's pushing these down. Okay, so let's go on to another one. This is ammonia. Ammonia has a lone pair on the nitrogen. And so in this case, we have 4 electron groups, 3 bonding, and 1 lone pair. So if we take a step back, we have 4 electron groups. Let's go to 3 bonding, 1 lone pair. So the electron, with the electron groups counted, it's tetrahedral with an angle of 109.5. But without counting this lone pair, see, it looks like it's just kind of like a spider kind of down. It's pushed down. That's trigonal pyramidal. So it's kind of a shape of a pyramid going down. Yes, the lone pair is still there, and it's pushing all of these down, but we don't look at that when we're dealing with molecular geometry. And here's another slide from it so you can see what it kind of looks like. Not kind of, but yeah, you can see what it looks like. So let's do a problem. We want to predict the shape of H2S. So the first thing you can do is do your Lewis structure, which is flat, so we don't know what the actual shape is, but we need to get the correct structure. So this is just breaking down everything that we need to put this together. Now we need to arrange the electron groups around the central atom to minimize repulsion. So we're going to try to keep this as far apart as possible on these. Use the bonded atoms use the atoms bonded to the central atom to determine the shape. So when we look at the actual shape of a molecule, we don't look at electron geometry. When we're asked about a shape of a molecule, we actually give the molecular geometry. Even though we count this for one thing, we actually go by this. Even it's kind of a weird thing, and I'll be honest, I don't know why. I would think that counting the electron pairs would be vital, but I don't know. It's just the way it's always been. I'm sure there's an answer. I just don't know it. So let's go back here. We have 2 lone pair. We have 4 electron groups, 2 bonding, 2 lone pair. So we have 4 electron groups, 2 bonding, 2 lone pair, and it is 109.5, and it's tetrahedral for electron group, but molecular geometry is bent. So it's similar to water, and that's what we're looking at here. Okay, so state the number of electron groups and lone pairs and use the VSEPR theory to determine the shape. So we have 3, and I think they're all on the same page, so I can't break these up. So I'm just going to show them and discuss them. It's a lot easier this way. So let's pretend we did the Lewis structure for all of these, and we break this down. This one has 4 electron groups. It has 3 bonded and 1 lone pair, so that's going to help you look that up. Water has 4 electron groups, 2 bonded and 2 lone pair. And then we have, and these are honestly the easiest. When you see that there's 4 bonds, they're tetrahedral. They're the easiest to, it doesn't matter what they're attached to. If they've got 4 bonds and no lone pair, they're tetrahedral. So 4 electron groups, 4 bonded, 0 lone pair. When they don't have lone pairs, they're a lot easier to figure out. So here is a chart. We're going to pretend we looked at it, and we're going to write down what we did. So I'm going to jump ahead. So with this one, we have a trigonal pyramidal. So if we look at it again, let's break it down. 4 electron groups, 3 bonds, 1 pair. 4 electron groups, 3 bonds, 1 pair. Trigonal pyramidal. Remember, we go by the shape is the molecular. So it's very similar to this one, which is right above it on the periodic table, if I'm correct. Water, we've already covered water, which is this one. And now we have 4 and 4. So if we go 4, 4, 0, it's tetrahedral, because I told you when there's no lone pairs, the geometry matches. And this is what it looks like. And this one here is methane, but this is carbon tetrachloride is what this one is called. And it doesn't matter because it's still the same. It's still in the same shape. So predicting geometry using VSEPR theory, we draw a correct Lewis structure. If you do not draw the correct Lewis structure, you're not going to get the right shape. Determine the total number of electron groups around the central atom. Determine the number of bonding groups on the number of lone pairs, because first you're going to look at the electron group, then you're going to actually separate it from bonding and lone pairs, and that's going to give you the geometry. I'm going to give you a Vesper sheet that you can print out that will make this easier instead of having to keep referring to this. And there might be one in that handout that I gave you, but I don't think so. Okay, so I briefly talked about this. It's in your book. This is how organic draws their molecules. We draw them with dashed and wedged lines because nothing's flat, so we do our best to show that it's not flat on a piece of paper. So again, if you have, some molecules will be flat on the paper. If it's hashed lines, it's projecting out of the paper. I know this is saying into the paper, but it's in the back. And this means out of the paper. That means in your face. So this is directly pointing at you. This is directly pointing in the back of you. And a straight line, this is in the paper. And here is a chart to give you an idea of all of the linear, trigonal-planar, bent, tetrahedral, and trigonal pyramidal, but I found a better one that actually, the green has the lone pairs so you can see them on there. And I think learning with the lone pairs is actually easier because you might forget them when you're first learning how to do this.